of articular cartilage in knee joint and endothelial glycocalexy in an artery using anisotropic porous medium. Sir, a very warm welcome to this program, sir.
Thank you.
You can take over the session, sir.
Okay, so good morning, Professor Deshmukh, also Dr. Mahalakshmi, and thank you very much for introduction, Dr. Pamela. So first of all, let me thank Professor Deshmukh for inviting me for this occasion. I'm glad that Department of Mathematics, Dayanand Sagar University is celebrating Sir Srinivas Ramanujan's birthday celebrations, but as a long colloquium sessions. I'm glad to be part of this. So now my association with Dayanand Sagar University, I was there a couple of years back as part of ISTAM, Indian Society for Theoretical and Applied Mechanics. So that was one time I visited, but not the main campus, probably the one which is in the city. So when I got to know the occasion, and I expected that the audience will be little heterogeneous. So therefore, the aim of today's talk is not to have some rigorous mathematics, theorems, proofs, or methods. Rather, it will be little elementary to some time. Maybe after some time, maybe we will also discuss a bit of mathematics. Okay, so this is considering the heterogeneity of the participants. So now, as you see the title, Mathematical Models for Tumor Growth Dynamics. Okay. So when you say tumor, yeah, people have reasonable idea about tumor, right? Yeah, some people can connect tumor with cancer. Some people think cancer means it's something else. So we can see little bit on what is its relation and what kind of growth dynamics, etc. As I have indicated in the abstract, initially we will have elementary dynamical models which are used popularly in the population dynamics, etc. That is applicable also to the growth dynamics of tumor. Okay, so outline mathematical modeling, little fundamentals, then also little advanced models, and towards the end we talk about some of our work. So let us know a little bit about preliminary information on tumors. When I say preliminary information, I mean to say what sort of the structure inside and all that. So what is tumor? It is nothing but the normal cells losing the control. Okay, normal cells losing the control. That means it becomes abnormal. Any abnormal growth interior to the body of a human or exterior, sometimes these are tumors. Okay, but only thing is early stage these are non-cancerous, so they are called benign. But once they cross this early stage, then they are malignant. That means they are cancerous. Okay, but today's world, if you see, even though we have a lot of advanced technologies, most of the times, very rarely people come to know when the tumor is at early stage, that is the non-cancerous stage. You might have heard from various contacts of various colleagues. Somebody got diagnosed this stage, that stage, cancer, etc. So that means these diagnoses will identify when it is a little at advanced stage. Okay, so that's one point you should. And also we have a lot of medical technologies at advanced stages. So this is, for example, an MRI of a brain cancer. You can see axial section is taken, and you can see this part. This is the tumor inside the brain. So there are techniques to have high resolution imaging and understand what is the dynamics with the day, and then see what kind of tumor it is. Okay, so these are very much advanced level. So now if you see to the left, this one is melanoma, that is a skin cancer, and this is a carcinoma which is in the intestine. You can see day 2, day 4, day 8, day 10. So the structure is evolving and then growing. So you have a colony of cells, they multiply and grow. So when you say size of the tumor is a small, size of the tumor is big, it means the number of cells inside the cancerous cells, they multiply and they grow. So then the size of the tumor automatically grow, right? So that is one point which you need to understand. Then the other point, you see the gradients, the kind of gradients you can see in the structure. So the cells, then interior, there is a small patch where you are not able to see the cells. So these gradients, so this area is proliferating region. So that means it's the advanced region, that is the tumor is growing and growing. And this is the interior where you have nutrients, oxygen supply, so that the cells multiply. But towards the interior, you are not able to see the cells. That is because it is a hypoxia region where the oxygen levels are very low. As a result, there is something called necrotic core is formed. So necrotic core means where the tissue is almost dead, therefore there is no support for the cells to grow. So therefore you attract something called necrosis. Okay. So now if you see as a cartoon of invasive tumor, so this is the invasive zone, that means the growth. So it is certainly not regular, as you can see. Typically we say it's a spheroid model, etc., but these are for our simplicity. Otherwise the growth dynamics is irregular. And at the periphery you have several capillaries. So these are the vasculatures through which within the human tissue you have blood-borne solutes, etc., are transported. And as I indicated, so this is a highly active proliferating zone, and as you go inside, zone of cell stasis, low in oxygen, that is a hypoxia region, and then this is the dead cell region, that is a necrotic core. So now if one has to understand the dynamics, it's pretty complex. The reason is you have interstitial spaces within these vasculatures, and the vasculatures have a conductivity, that means they are porous. Through the walls, whatever nutrients come up through the vasculature walls, they are delivered into the tissue, and the cells multiply, then the vasculatures also grow because it's a human body, so it's a very lively, so a lot of things grow. So it's pretty complex to model complete picture. So this is one point I need to tell. How complex it could be. See this, this is the image of glioblastoma. So that is brain tumor. Okay. So you have these vessels. So these are the blood vessels. So the network is quite complex. So hence it's very difficult to capture the complete dynamics. So therefore, what is the fundamental modeling approach? So that's the question. Because people started initially with the simplest models, and then slowly today you have complex models. Okay. So now if you see further a cartoon diagram just for the people to understand, there are healthy cells, there are dead cells. So these saffron type are healthy cells, and then this chocolate type are dead cells, and this is vasculature. Okay, just for the cartoon sake, I have put so many vasculatures. But if you see the percentage, the cells up to 65%, vasculature, you see the pipes only up to 5%. That means the cells are the vasculatures are very low. So if you want to treat somebody, whatever the drug, it has to be get transported through low proportion of these vasculature. Therefore, its advanced stage means already some cells are died, and then whatever drug you give, it may not work. So these are some challenges. And interstitium, that is nothing but the empty spaces where some tissue, etc., is there. Okay. So this is a cartoon structure if somebody wants to visualize. Okay. Semi-necrotic, then core interior necrotic, and periphery region. Okay. And how do you classify? So one is in vitro analogous. That means you have a tumor in isolated, okay, configuration, and another is in vivo. That is, it is surrounded by a normal tissue. In vivo, it's understandable because it's inside a human body, let us say. So you have a lot of normal tissue surrounding such a tumor. But what is in vitro? It's a kind of a laboratory frame. So when I say laboratory frame, what people, the biologists, clinical practitioners do, they want to test various drug impact. They grow purposefully cancers in mice and various experimental animals which are acceptable, and they try to observe the impact of the drug, sometimes interior by imaging, and sometimes they need to do various other experimentation. What they do, they take out the tumor from the body, but not completely. They take out in such a way there are still some vasculatures are connected. So then they do some experimentation and then they put it back into the body of such animal experiment. So this is in vitro analogous. Almost it's in a laboratory frame, it's a fitted. Okay. So these are two classifications. So now with this preliminaries, I would like to move to the dynamics. What kind of dynamics? As I already indicated to you, we will start with very elementary models which are popularly used for general prey-predator models, population dynamics, etc. Okay. So how these dynamics, tumor dynamics happens? The simplest is cell doubling. That means you have one cancerous cell, then it started growing, and then it's multiplying heavily, so leading to exponential growth. Okay. Other one is, see, if you see exponential growth, then you should observe tumors are very big, and then it's larger than some human organs, or sometimes larger than some of the parts of the body, etc. But that doesn't happen. So that means there is somebody sitting and controlling the growth, right? So that dynamics also one has to look into it. So there is a slowdown process. That is the second point. So exponential model, then it's a bit controlled model. So that's a logistic growth model. Then the next part is the spreading and invasion with the complex interaction of the tissues, etc. Okay, so that's little advanced modeling. Okay, so these are the dynamics. Now, how do you study, and what is the need of modeling? So the need of modeling is to give kind of some recommender systems for the clinical practitioners and minimize the experimentation in some sort, right? So one can do studies with a large time scale. This is one aspect. Another is slow scale. So that is sorry, there's a typo, transport scale. Okay. So large time scale, that means you are seeing for days and then see. Another is a small scale. So you just see on just limited period. Okay. So this is one aspect. Another is identifying critical issues based on various parameters. So that's the key point of mathematical modeling. So then what are the approaches? Discrete approach. When I say discrete approach, you visualize tumor as simple colony of cells. Okay. And then you observe them discrete growth of colony of cells. That is one. That is micro scale. So that is a micro scale model in some sense. The other one is continuum approach. That is, you are looking at it at a large distance. It's a global picture. So it's a macroscopic, right? So I hope one is microscopic, you're seeing closely. Another is from a large distance. That is a macroscopic. Now, what is the difference on this scale? What is the difference on this scale? You will see, okay. So now let us see the first simplest model. That is, many of you, those who have studied biology from elementary classes, you would have heard of Malthus, right? So the Malthusian models are typically used for population dynamics. And this is very simplest model. What are the assumptions? This assumes that the population is no mixer, it's just homogeneous, and it's not in control of anybody. So it's in isolation, okay? And resources, etc. So these are not influencing, okay? And it's a pretty comfortable population. So for such a population, if you try to model, then you see there is no control parameter, resources are plenty. What will happen? Obviously, you will have exponential growth. Okay. So you see, Thomas Robert Malthus is not a mathematician. No? So that's an interesting point. Not only economist, of course, as economist may be using some mathematical models, but a priest as well. So discrete approach, when I say you are just looking at individual cells and how the cells are growing. So the rate of growth of cells could be growing with some rate and could be also decaying at some rate. So growing, we have a positive sign, decaying, we have negative sign, right? So now there is a competition between these two. Suppose if you call alpha minus beta is lambda, then naturally, depending on the sign of lambda, you will have the corresponding growth or decay. So it depends on the competition between these two. So accordingly, if alpha is less than beta, okay, so then the population is decaying. If alpha is larger than, then the population is growing. Okay, so it's the simplest Malthusian model. But as I indicated, no population can grow exponentially because there are constraints. So that is the reason you see the number of tigers, for example, in Asia region, how many, etc. So those census can be obtained by fitting various parameters alpha and beta. So the next model is controlled. That means there is a limit to it. Okay, so that is called carrying capacity. It is based on logistic growth curve. Okay, so this is due to Francois Verhulst. Okay, of course, here he is a mathematician. So the population, this is the carrying capacity. That means the maximum saturation level. That is the. So then, from initial population, how it grows. This is a typical logistic growth. So what do you mean by this? How do you look at it? Okay, how do you look at it? It is related to the carrying capacity, which is the maximum population size of a species, given the resources, whatever given under those. You're not controlling those. Okay. So then initially there is a slow growth, then there is a fast growth, and you're touching saturation, then naturally you will plateau, you stabilize. Okay. The key point here is you can reach here like this, you can reach here like this, you can also reach like this, right? So who is controlling this? The rate of attaining saturation. Okay. So naturally, in this case, the carrying capacity is changing. Okay. So if you have a fixed carrying capacity, then it will be like this. But carrying capacity may change. So if the carrying capacity is changing, then we expect the rate also changes. So what is the corresponding dynamic model? The rate of change depends on the size. When I say size, yeah, you can visualize when I say size, it is the size of a tumor or the total number of cells within the tumor. So these two are just back and forth misused. Okay. So therefore, the rate of change of the population, earlier we have seen it's a constant multiple of the population, but here you have a growth dynamics which is varying. So that is again function of size. Okay. So depending on that, you arrive at a dynamic growth model. So here it is just depending on the size, whereas here growth not only depending on size, but it's relative to the carrying capacity, right? So that means you have some resources, and then the maximum allowable is this. This is a limit K, but the size is very small. So then the dynamics is different. On the other hand, suppose the size is pretty large, and then the carrying capacity allowable is very small. So then it will explore, and then okay, it will go to exponential. You see, if carrying capacity is pretty large, then it will go to the constant exponential growth model. K goes to infinity. Okay, so these are the elementary dynamic model of tumor growth. As you can see, lambda is controlling, okay, the rate. So lambda is controlling. If lambda is low, then the delay is more. You see, the to attain the saturation, it takes time. If lambda is large, then yes, it goes, and then it touches the saturation very quickly. Okay. So what do you mean by the saturation, and why it should attain a saturation? Yes, so why it should attain a saturation in the sense, as time progresses, the cells, some of the cells are dead. Some of the cells are dead. That means there is no possibility of further growth. Slowly, it will be stabilizing, and then the supply of nutrients is not there. Okay, this is in the context of tumor. But if you want to interpret the same in terms of the typical population balance models, that will be slightly different. Okay, so that means the allowable resources, everything are consumed, and then it will attain a saturation in terms of typical population. Now, there is a lot of dynamics. I already indicated to you there is a vasculature, cells are interacting with vasculature. So Ahrenfeld and colleagues, they came up with the model. Look, your carrying capacity may not be constant. Your carrying capacity may be varying with time. And how it is varying? As a human body, in the tissue, the vasculatures also grow. They change with time, the vasculatures. So therefore, there is a stimulation of new vasculature and the cells are interacting. So this is the angiogenesis interaction. And the other one is there is a inhibition due to the existing vasculature. Okay. So this is the new vasculature is coming, assisting the growth of the cells. Okay, the rate capacity is also enhanced, whereas the existing, may I request colleagues to be on mute, please. Yeah. So
ready to occupy, right?
Excuse me, may I request you to be on mute? Thank you. So this is already existing vasculature, and the cells are interacting. So therefore, there will be little compression of the vasculatures, and they lead to lack of nutrient. Therefore, they oppose, the carrying capacity will be reducing. Okay. So if you see this plot, the carrying capacity is like this, and the population based on the this model. That means it's a combination of this growth model where K is changing. So then it will be like this. So this is the tumor size. As I mentioned, size of a tumor or number of cells. So it is okay. So this is a mm cube. Okay, it's a volume in that sense with the days. Okay. So this is the typical scenario. So these are not original work. I told you it's a review because heterogeneity of the audience. So my aim is to introduce you to basic theory, and towards the end we will show some of our contributions. Now after this, shall we stop? We won't stop. When you have a tumor coming, etc., what do? We start our treatment, right? So now when you start your treatment, how it is impacting without, see, one is clinical study, another is, yes, we should do mathematical modeling and give a recommender system of any treatment, right? So therefore, let us talk about the treatment. Suppose you have a diagnosis and you have identified there is a tumor in a body at particular stage. Then what do? You start drug treatment. What is the expectation? The expectation is the drug treatment will kill some of the cells, if not all, right? So with that treatment, if you see, this is little varied logistic growth, but on a log scale, right? So the moment you start treatment, you expect the cells should be killed. So this is anti-tumor cell kill model where you have a positive parameter and that is controlling the drug, okay, in some sense. Then this is this model takes care of once you start tumor treatment, the rate is reducing. Okay. And another is anti-angiogenic treatment, where when I say angiogenic, always the cells are interacting with the vasculature, etc. So for example, you start a chemo, then the carrying capacity will be reduced. What do you mean by carrying capacity? Suppose you have a tumor in lungs. You have a nice tissue, lungs contain a lot of smooth tissues. So the carrying capacity is more because it's good to the tumor to grow. But the moment you start some kind of anti-angiogenic treatment, then we expect that the carrying capacity reduces. These two I talked already. Now this is the additional due to the treatment. And how the treatment chemoimmunotherapy, there are some mathematical models where this is the A of tau is the rate at the onset of treatment, and CLR is the control rate. Okay, so with respect to time, okay, with advanced time, what is the control rate? Okay, so this is as a mathematician, how do we fit this Xi? Maybe it's not in our hand. So you have to talk to the clinical practitioners, understand the biologists what kind of drug and what functionally it does on the cells. You have to understand, and that character can be modeled into this slide. Okay. So now this set is the new model in the sense this is typically taking into account the tumor treatment. Okay. So now with this tumor treatment, you can see it's reducing. If xi is given 0.1, 0.2, then correspondingly the size of the tumor, how it is varying. Okay, so these are the references. Okay, so those who are interested, they can of course see these little more details. Now this is a discrete approach completely, right? When I say discrete approach, we are just looking at number of cells, closely microscopic, and we are repeatedly talking about rate of change of number of cells with time. Therefore, we have only ordinary differential equations. And what is the drawback of this? There is no spatial information. And there is another important thing which is not captured here is once you have a primary cell and then it triggers the substantial growth, the corresponding signaling of the cancerous cells will invade into other zones of a human body and multiple cancerous locations are formed. So that's quite possible. So the particular ODE approach is not able to capture. So therefore, we need to improve. So hence we go towards the partial differential equations. Why? It's not just time. You also need to take into account the space. So those who are interested, they can refer J.D. Murray. So he has done a lot of work, including books. Now in spatial approach, what we are trying to model is, suppose you take let us say some still water and put some dye color. Water is stable, still it's not moving, but you put some dye. What will happen? The dye naturally spreads. How it is spreading? It is because of the diffusion. Okay, so it's just a diffusion. There is on its own molecular interactions. So this is a motility. And similarly, the rate of change of tumor cell population depends on the local phenomena, and then there is a net proliferation of tumors, the invading. Okay, so they're moving. So that's kind of the corresponding reaction, etc. You have to take into account. So the first, based on this law, that is the rate of change of tumor cell population is the net flux, that is the diffusion flux, plus the net kinematics, either proliferation or death. Okay, so but here since we are talking about growth model, yeah, I'm showing plus lambda, but you can debate on the sign of lambda. For example, in terms of reaction kinematics in any chemical, this is called reaction rate. Lambda is called the rate constant. So the tumor cell density, diffusion flux, then the proliferation. Typical diffusion models are the Fick's law of diffusion. You can say Kirchhoff's law in electricity, etc. So everything follow the same. What is that? So this is a diffusion coefficient. That is the character of the intermolecular or the intercellular dynamics. That is active motility. So the rate of change, J is rate of change of the size or the number of cells with space. Okay, so that's a flux. That means if you take some element within that, how much the flux is coming. Okay, so in one dimension, I've kept it in one dimension. So Here J, I have shown it in bold because we will see that's a vector actually. So here purposefully I misuse the notation. Now once J follows the fixed law of diffusion, of course here I am assuming D could be D could be varying because it depends on where you are diffusing. Okay. So this is PDE now. It's no longer ordinary differential equation. It's a partial differential equation. Okay. If D is constant, then we can pull it out, and then you have much simpler, because if D is varying, then it's slightly difficult to solve. So now if D is constant, then you have this simpler PDE. It's a linear PDE. Yeah, so one can solve if the geometry is nice, one can solve analytical methods. Okay. So now let me move to the same thing in 2 dimensions where J is a vector. So then J is following fixed law instead of dc by dx. Now it is gradient. Then if D is constant, so it is just for those who are interested, I am just showing. You can model such growth dynamics, drug transport, etc. using such simple PDEs as well. If you ask some master student, those who have done first course of PDE, they can attempt an analytical solution. So this, as I mentioned, the cell inside the tumor, we are modeling with typical population balance models. For example, the same model is used for the census of the rats. Okay. So this is from my colleague, actually my friend has given a notes. So from that muskrats spread is being studied using this model, and what is the corresponding solution? Corresponding solution follows this Gaussian distribution. Okay. So these are some connections of typical population balance models versus the tumor cell dynamics. So there is a quite good correlation. So now typical, if you talk about tumor, we are for mathematical convenience, we say it's a ball, it's a spherical ball. Okay. So in 1 dimensions, if you restrict radial distribution, radial growth, it is expanding like this, then we restrict to R, the Laplacian, whatever seen in the previous slide, it will be reduced to this. Then you need some boundary condition, then some initial condition, then one can solve. Okay. If it is varying diffusivity, then there is a competition between diffusivity and the proliferation rate. Okay. Who will compete? Who will win? Okay. Depending on that, the growth dynamics change. So from rich mathematics point of view, analytical solutions are possible, semi-analytical, asymptotic solutions, numerical solutions, and complete existence uniqueness results are also possible for these models. When I say existence uniqueness, it's a lot of theoretical PDE, it's possible. Okay. So for example, when lambda by D, they are hand in hand, that means they are of the same order, then the concentration at different times with radial, so it is like this. That means at any cross section, when the time large time, okay, you have a low nutrient, because it's both are hand in hand, that is diffusion and proliferation rate. So therefore it's reaching the boundary value. Okay. You have initial value and then reaching the boundary value, because the boundary condition is restrictive. Okay. So this is one, but suppose you don't have the similar order, they are competing. So when lambda by D equal to 1, we have seen, then lambda by D is greater than 1. and then play with it, you can. Okay. Now, the kind of technology that is available, you see, these are not MRI images. These are typically obtained from imaging techniques. Okay. So that means they have taken some images, true images. From there, they mapped using image processing tools, and they have reproduced. So the initial location and then how it progresses with time, etc. Okay, so this is diagnosis time, and this is death, different views. Okay, so these are very helpful also for imaging techniques. Now, chemo also can be modeled here. So you can see initially we talked the similar model. So this is the diffusion, this is proliferation, and then this is chemo. Okay. So you can study rich mathematics, etc. Okay. So even though the equation looks elementary, it's quite complicated to solve sometimes, because if D is varying, then it gives you a lot of tough time. Okay. So now that's all PD approach. I have shown you only time and then space. And is it that? No, you can further go to little more details. What are they? So typically in your lumen, etc., when along with the blood flow, there are excess H+ ions, and they degrade the local tissue. Okay, if there are excess H+ ions, sometimes they are flushed out through the lymph vessels, but sometimes if they are deposits, so then they hinder the cell diffusion and proliferation, and then there is a degradation of local tissue. So this also is important. So now we are having more combinations of the picture. Okay, it's not just the cells we are talking. Now we are increasing the complexity. What is that? Yes, cells. That is nonlinear diffusion and logistic growth. H+ ions which diffuse and production or decay. Then the extracellular matrix. When I say extracellular matrix, what is this? You see, you take an example of cancer in lung. Not only cancerous cells and vasculatures, there is other tissue. That is the extracellular matrix. That also will grow sometimes, it will degrade depending on the necrosis formation, etc. So now we have increased the complexity, and correspondingly we model. So if you model, then you can see it's no longer just C. You have 3 components. It's almost, we are ready to discuss about multiphase model. This is cells, nonlinear diffusion, logistic growth, then H+ ions diffusion, and then this is proliferation and death. Then this is extracellular matrix, logistic growth, and then this is the death. Okay. Now these are coupled PDEs. Solving is much more difficult. If you try for analytical, it's almost impossible to get any analytical solution for this. You have to go for numerical. And of course, if you want to develop some theory, it is fine. So when our colleagues contacted me that this is on the occasion of Sir Srinivas Ramanujan, I could not, because I am not expertised on his works, but I thought, let me try something to relate with his contributions. So I made an attempt, but kindly excuse me because of my problem with my hand right now. I'm not able to type. So I have given a handout. So that I will try to show you in a minute from now. What I'm trying to say is, this is a dynamic system model. Assume these are approximated, and instead of Laplacian, it is just some M1 minus M2, etc. So it is nonlinear coupled dynamical system, right? So then I spent some time whether Sir Srinivas Ramanujan did he make any contributions to such systems? And surprisingly, I'm very happy to share with you that such contributions are also done by him. So now I'll just show you in brief, because my aim is not to discuss the complete math. My aim is just to show you that whatever the dynamical system which we have seen while modeling tumor, that can be correlated to Sir Srinivas Ramanujan works. Okay. So what he has done, he has introduced this Eisenstein series. Okay. So these are series, you can see, okay, infinite series. Then he has shown that these series satisfy these differential equations. Okay. Of course, at this stage, I cannot conclude that this is a similar to our system which we have seen just. Which system? Yeah, it is similar to this. No, I cannot. The reason is, you can see there is the independent variable is multiplied. Independent variable is multiplied. You see here, what is the dependent variable? C, M, and mu. Independent variable is time and the space. Okay. But here, if you see, the independent variable Q is at two places, right? It is explicit, whereas in earlier equations, nowhere time was explicit, right? But then we can convert. So these colleagues, Hill and colleagues, they have shown that if you make this transformation, you can see now what is the difference between this system and this system. Here, independent variable is explicitly visible, whereas here the independent variable, which is time, is not explicitly seen. Therefore, it is just nothing but a nonlinear dynamical system. Okay, it's a nonlinear dynamical system. So I am pleasantly surprised that Sir Srinivas Ramanujan has contributions to the differential equations in this form, which is a dynamical system. Then further, one can show that if you use this transformation, it's a simple algebraic calculation. Use these transformations, compute dp1 by dy1, then you will get whatever right hand side with P and Q, similar structure you have received P1 and Q1. That means this transformation is keeping these equations invariant. Okay. This transformation is keeping these equations invariant. Why? Because you apply this transformation, still the equations remain the same. Only P1, Y1, that's all, Q1. Okay. So you can show it for other two as well. So this is one invariance. This is very good for PDE theory people. Once you have this invariance, they have suggested this parametrization and obtained differential equation, which is called Riccati differential equation. This R is of Riccati type. Okay. So this is one learning I have done after our colleagues contacted me for this talk. I'm very happy about that, to realize that Srinivas Ramanujan had also contributed to these kind of things, which I am personally happy because I can correlate to our tumor dynamics and then discuss a bit. Okay. So now let me come back to the other talk. So Riccati equations, once you have, you can study theoretical results, explicit solutions, asymptotic solutions, and then identify applications. What I have seen from literature, these equations which are obtained by virtue of Srinivas Ramanujan's series, these have applications in number theory, but now I realize that it has applications in tumor as well, right? Tumor dynamics. Okay. So now we go to the pre-final section, mathematical modeling of tumor multiphase models. Okay, already I indicated to you multiphase, but here the context that I am talking multiphase is slightly different. Okay, so when I say slightly different, I have mentioned to you So far, whatever we have seen, it is just a dynamic model as number of cells, number of H plus ions, number of extracellular matrix or volume. Okay. We have not discussed the transport, say nutrient or say drug transport as a fluid mechanical system. Okay. So this particular section is talking about this new dimension, that is typical tumor dynamics can be seen on a macro scale, that is from large distance. It is a homogenized. That means all the complex structure you are not bothered. You are simply saying there is one solid phase and one fluid phase. That's all inside the tumor. And let me see from hydrodynamics perspective, that is from fluid mechanics perspective. So that is this model. So what we are seeing here, conservation of cells, that is, you can say solid phase and fluid phase. So you have two phases and two phase Freud model. This is a colleague from Oxford University. So we are collaborating. So I took liberty to give this work of hers, which is already published. Okay. So now when you talk about fluid mechanics, you have to bring conservation of mass and balance of linear momentum. Okay, as the governing equations. So colleagues who are not comfortable with this, kindly excuse me, because I kept this talk like two parts. The part one, so far whatever we have already discussed, it is a bit elementary, so that anybody can get a little bit of idea if they know what is a differential equation, right? But now slightly we are moving to some technical. Okay. So here phi c is the volume density of the cells. Phi e is the volume density of extracellular fluid phase. Then Vc is the velocity and Ve is the velocity, corresponding velocity. Then this is the source. Plus sign is the source and negative sign is the sink. Okay. So what is Sc is net growth and death rate of cells, depending on the sign. Already I have mentioned. Now we have a saturation assumption. What is the saturation assumption? The saturation assumption here is the total volume of both the components remain the same. That is phi c plus phi e is a constant. Okay. So with this assumption, saturation, if you combine these two equations, you see a simple conservation law. This is called equation of continuity for incompressible fluids. Okay. So that is fine. It's not moving. Yeah. So then we talk about momentum balance for the cells. Now here you have a fluid phase exerting pressure on the tissue and tissue is deforming. So it will give a reaction back. Therefore, there is a relative velocity coming into picture and that is balanced by the pressure. Okay. It's difficult for me now at this stage to completely explain. Okay. So yes, this part, please excuse me. So this is for each of the phases, corresponding momentum balance, then the drug transport. So what is the difference between the earlier, these equations and this equation? These two equations are capturing the mechanical behavior within the tumor. What do you mean by mechanical behavior? Fluid is making some work on the tissue and the tissue is also working. So there is a mechanics happening, fluid mechanics happening and the solid mechanics happening. Rather, it is just a continuum mechanics on a big picture. So that is this. But together there is something else happening. What is that? The drug transport, solute or nutrient molecule transport. That is a typical diffusion reaction equation. We can add a convection as well. Okay. So here these colleagues have considered these models as a spheroid and they fit some boundary conditions. Okay. With that, let me It's a simple radial model. All the complexity is reduced to one dimension. Okay. And this R equal to 0 is origin. There are no source or sink. And the boundary is moving. You see x of t. It's proliferating. Its tumor is moving. The x of depends on the time. Okay. Therefore, the boundary condition is velocity of the cells is varying like this. Now this introduces complexity. One has to solve for x. It's a moving boundary value problem. Okay. It's a simple model, 1D model, but unfortunately, it's a moving boundary value problem. So that makes the life complicated. And they have solved. And you can see with time and R. So this is development of a tumor to a non-necrotic steady state. Okay, there is no necrosis, a simple steady state, and the interface x of t is varying like this. After some time, it's stabilized. Then RC of t is the interface between the cell birth and cell death. So there is interface, that is a critical radius. Okay. Suppose you are also including necrotic, then there is an additional component, that is L of t, that is an interior, deep interior, the tissue, the cells are dead. So how that is varying, you see, beyond some, it's quickly stabilizing. Okay. After some time, all the dynamics, they reach the steady state. Okay. So that means there is a dead cells, and then there is no further growth, and all that, it is stabilized. Okay. So the model is very simple, but now why we have to study the math? I already mentioned we have to give a recommender system, right? But what kind of technology? If you restrict to only ODE, PDE models, then maybe it's too much of a restriction. We will be theoretical. We won't be able to give more practical recommendations which are useful to the real practitioners. So therefore, one has to also rely on other techniques. So this is a nice paper review, but it is talking about imaging data. So they have modeled, again, it's a PDE. Okay. P is proliferation of cells and Q is quiescent phase. That means it attained some stabilization. Okay. Where gamma is the rate at which the nutrient is controlled, and that is related to oxygen concentration, and there is a hypoxia threshold. This user will define. That means given the region of the tumor, the clinical practitioner will tell, you see, if the oxygen level is below this, you declare this is a necrotic region, this is hypoxia region. So this C height is depending on the practitioner. Okay. So now what they have done, they have taken this model and proposed an inverse problem by taking the data. So this is the true images, and these are constructed based on the image processing tools. These are the lateral cross sections, and this is a view from one angle. And you can see they have taken imaging of this picture and then given it to an inverse problem PDE solver, and they have got this picture where the necrotic core region and then proliferating region, how it is coming. So the point that I'm trying to show here is, it's not just a PDE models. You have to integrate with various other existing models. Okay, so then you can give recommendations which are more close to the reality. Otherwise, you give something and then something else happens. Okay. Now, what is our contribution? So we have also done some rigorous mathematics to not to forecast the growth dynamics, certainly, rather to identify parameter combinations which will onset the necrosis, okay, in a tumor. So this diagram already I have shown. So I'm not showing the math because it's a lot advanced modeling, fluid mechanical models. So therefore so my aim in this talk is not to show you all those. So if you see the interstitial fluid pressure with time, and R is 0.1, R is 0.3, it's normalized. R is 1 means it is the boundary of the tumor ball. R is 1. Then low values of R means it's interior. Okay. Now what it is showing, if you are interior to the tumor, the interstitial fluid pressure is very high. And as you come along to the periphery, the interstitial fluid pressure is very low. Okay. So these recommendations are very important. Okay. Why it is important? Suppose you are injecting some directly into the tumor, you are injecting something. It depends on the pressure distribution, how this particular drug reaches and what part of the tumor it will reach. So these are difficult to see. Okay. So it depends on the interstitial fluid pressure. Therefore, you should know, and you should also know where it is convection dominated and where it is convection suppressed. Why? If you have a convection dominated zone, if you inject some drug, there is a possibility that it gets convected and reach to the tissue, reach to the cells, so that it will attack. Suppose it's not convection dominated, then you inject, then it has to go only by diffusion, which is not sure whether that far it will reach. So therefore, we try to identify. And the other is parameter combination, where the drug is not reaching. That means it is necrotic zone. So this is with the radius, and this is the concentration of the drug, and this is the radius of the tumor, normalized 0 to 1. Suppose somebody is declaring, if my nutrient level is below 0.3, I will call it necrotic. Then you drop a horizontal line. You drop a horizontal line. Then these values corresponds to necrotic, and above that line, these are non-necrotic. I hope you're following. Suppose somebody tells, no, my nutrient is below 0.2, I will declare it as necrotic. Then you drop a line like this, horizontal line. I should have done that. Then here, this curve is corresponding to what? This curve is corresponding to some reaction rate. Okay, yeah, this one, phi is 5, and the radius is, that means what you're trying to say is, suppose up to here you drop a straight line and then you drop a vertical line. This is a necrotic region you will declare. Okay, so this is one which is very important. And finally, as a mathematician, if we do something, we have to tell, yes, look, I have done something, but whether it is practically viable or not. So fortunately, we got some clinical studies where these colleagues have grown tumor inside mice, and then they have given doxorubicin injection, and they have put it under luminescence microscopes, and they see the density where this drug has been transported into the tissue. If it is not going interior, then this is the necrotic zone. So our mathematical modeling readings are pretty much qualitatively similar. There is a difference. The reason is the parameters that they have taken are completely different, and they are not so much micro level. Islet radii, etc., are not available to us. So therefore, this is one confidence that we get. Mathematical models are also important, so that we can correlate with clinical studies. Then we can believe on the mathematical model, we can improve. So this is some of our contributions on Journal of Theoretical Biology, where we discussed just now whatever the plots I have shown you, they are here. It's a macromolecule transport. That means the tissue is deformable, then fluid mechanics interaction, then the drug transport we have modeled. Okay. Here we have done a complete mathematical analysis. That means it's a theory, theorem, proof, lemma kind of. What we do here is we take the corresponding model equations, discuss the existence, uniqueness. Why it is required is suppose you are trying to do some numerical simulations for irregular geometry of the tumor, then you should study such mathematical analysis. And here also we have discussed explicit models, closed form solutions, and those who are interested, they can. Yeah, these are some of our contributions. So now concluding remarks, as I mentioned, it is very, very difficult to capture the complete dynamics. It's a moving boundary value problem. If somebody wants to plan it, minimum it has to be modeled as a moving boundary value problem. Then you understand the parameter combinations carefully with the corresponding biological context. Then only we can give good interpretation of the results. Then once you do that, you can fix the threshold values of the parameters which are adaptable to the clinical results, and it becomes a good recommender system. Okay, in some sense, it's a kind of training model. Training data sets can be generated, large number of data sets, and you can fit the current day deep learning models, etc. Analytical models do not suffice beyond simple. Yes, that's analytical tools. No, it's only simple cases. Beyond, not possible. So therefore, it is very much required devise new techniques so that you assess the treatment much ahead of the trials. Okay, that's important. In order to achieve this, cross-disciplinary groups play a vital role. When I say that, a lone mathematician cannot do, a lone biologist, clinical practitioner cannot do, or a chemist cannot do. So you need a combined collaboration. Yeah, here we try to get in touch with one of our, okay, that's not here. We have a colleague with whom we have collaborated from biotechnology, and we published some work. But these are very elementary mathematical models, whatever we have done. So there is a lot to do to achieve whatever I have just shown. And thank you very much for kindly listening. And if you have any simple questions, I can take it. Thank you.
Participants, any questions? I think no questions from the participants.
Anybody, if you have any questions, please.
Deshmukh sir? Imtiaz sir, please unmute Deshmukh sir and Banga sir. There's one question from Keshav.
Please.
Can you suggest a textbook for this?
Textbook for tumor modeling.
I hope so.
There is no set textbook for tumor modeling. There is a lot of literature on published research papers. Yeah, there is no textbook. Yes, but if you want the typical population growth models, etc., then J.D. Murray. J.D. Murray is one. I'm sorry, I should have kept some references, but I have given in the running slides. And yeah, J.D. Murray, the title, I have to check the title, I don't remember. But if you see J.D. Murray, then you get the title. Okay, so a lot of population balance models are given, and you get some idea.
One more question is there, sir, from Rajiv. How these efforts has helped in clinical setting?
Yeah, as I mentioned, clinical setting is completely different. Therefore, if you do any modeling, then you have to understand what are the parameters in our mathematical model, whether they make sense in the context of a practice. Then you give a meaning to that, and you have to control whether this parameter should be positive, this parameter should be negative, and whether this variable will be linear or whether this variable will have a growth, all those things. So the model that I have shown in one of our papers, not model, the result. Yes, we have tried our best to compare with the clinical result. So our model is macroscopic, that is big picture. But the clinical trials, what they have done is with the tumor islet radii. That means there are small cells with different radii. So they have considered that. So we have taken some correlation and then we tried to see what happens. So we got qualitative behavior. So one has to read biology. Yeah, for example, my PhD student who worked on these related, up to 2.5 years, he did not start his work. 2.5 years, he was reading various literature, trying to understand the biology part, presentations, so that we are in a better position. Yeah, so it requires understanding.
Sir, one more question is there, sir.
Yeah.
Can we relate heat transfer with the growth model?
Not relate, you can include heat transfer in the fluid in the corresponding tumor dynamics. That means so far I have shown only the drug transport. Now you want heat transfer. That means under the heat transfer considerations, how the tumor grows, etc. Yeah, you have to give a coupling. It's possible.
One more question, sir, from Keshav Kumar.
Yes.
Sir, can you throw some light on optimization technique for cancer treatment?
Okay. Suppose you see, once you have a tumor, then I told you interior, it could be necrotic, right? Now, who will decide what is the level of nutrient and what is the allowable radius? You say it is necrotic. So this is an optimization problem. So you optimize C, where C is the nutrient, as a function of space and time, subject to the constraint that your convection parameters, say Pecla number and reaction dynamics, Thiele modulus, etc., allowable, you fix it, then that becomes an optimization problem. Okay, so it's possible.
Okay, sir. Deshmukh sir, you have any questions?
Yes, I would like to thank Professor Rajshekhar for such a brilliant talk, and in particular for pointing out the Ramanujan system of differential equations and how they impact our understanding of dynamical systems. That's something which maybe experts know, but for a layman like me, it is a very new thing that we learned about Ramanujan's work. I will not only like to congratulate you for solving such complex boundary value problems with moving boundaries, but I have one layman's question, if you do not mind, because when you're working with population dynamics, how does one know that one can use differential equations and equations based on continuous functions rather than discrete dynamics, because some of the population dynamics follows discrete jumps and not continuous.
Yeah, so thank you, Professor. So yes, these are typical, what I have shown is for a general lecture, right? And also I don't work so much on population growth models, but coming to your question, yes, we have to understand the variables. That means what is happening to the population, what are the impact parameters, what are the growth parameters. Then we have to incorporate sometimes functions like Heaviside functions,
Yes.
Times Dirac delta function,
Sure.
where there is a blow-up solutions, and most importantly, if you want to model the current day complex scenario, you need stochastic nature.
Yes.
So you have to include random process and then model. Then they will be like you have the modeling part, and then you have the corresponding statistics integration. Then you have to give recommender system 1, recommender system 2, and validate. And so that's how. So continuous will not give smooth
Yes.
solutions, will not give
Yeah.
a realistic picture. That's
Yeah.
why I said the existence uniqueness results that we have shown, they are in very irregular spaces of Sobolev spaces where you have a lot of irregularity. So
Yes.
we have shown. So you
Yes.
need to consider those, because you need to discretize. Then when you discretize, the domain may not be regular. For example, the imaging, I have shown you the images. They are very irregular. The core is irregular. So if you want to study, then you have to discretize using some complicated Galerkin methods.
Yeah.
So to understand that, you have to. This is one aspect. Coming back to again your population balance models, yeah, no, continuous will not give. You have to include the discontinuous functions. You have to include cutoffs. Suppose
Yes.
some after some stage you have to completely remove this function. So cutoffs. Then you have to introduce stochasticity into the model. Yeah.
Sure. Yes, it is a very complicated problem indeed.
Yes. Yes.
It's amazing. Wonderful talk, sir. Thank you very much.
Sir, one more question is there
Please.
from Arul. Sir, is there any article related to tumor dynamic and stochastic process?
Yes, I think there is work, tumor and stochastic boundary conditions, stochastic models. Yeah, I cannot immediately. Maybe I will write to the organizers. These, if you can share the question, then one is somebody asked book. I told JD Murray with the title I will share, and if I have PDF, I will share. Second one is this question, what you are asking, articles on stochastic
Tumor
models,
dynamic.
Geomar. Yeah, please write down. I will.
Okay,
Sir?
Any more questions?
Please.
Sir, this is Mahalakshmi. So using these models, can we predict the decaying nature also, sir, if possible?
Yeah, means it's a, for example, wherever lambda c minus lambda c, that will reaction take decaying kinematics.
Oh, okay.
Yeah.
Thank you, sir.
Yeah.
So we have been very fortunate to have you here, sir. So once again, I thank Dr. Dekshmukh, sir, for giving you a reference and bringing you here. So I take this opportunity on behalf of organizing committee. I would like to propose our gratitude and respect to your distinguished guest speaker, Dr. G.P. Rajshekhar, for not only sparing his invaluable time, and also in spite of his health issues, also he accepted our invitation and enlightened us with this commendable talk. Thank you very much, sir. Kumla
Thank
ma'am,
you. My
is there
pleasure. I
any
hope
questions?
you participants could get something. Okay. Yeah.
A wonderful talk.
Sure,
We
sir.
must have you over here for a personal visit for Mr. Rajshekhar sometime.
Yeah,
Yes,
sure.
yes.
I look
So we
forward.
would like to have you in our campus.
Yeah.
I'll be
Goodbye
happy.
for now.
Yeah. Thank you very much. Once again, thank you all for giving this opportunity.
Okay,
Listening to our.
Yes, sir.
Goodbye.
On behalf of our organizing committee, I thank Dr. G.P. Rajshekhar, sir, for his wonderful talk on modeling of tumor growth of cancer tumor cell growth. And I take this opportunity to thank our management, Dayanand Sagar University, for their kind support. I also thank our Vice Chancellor, KNB Murthy, sir, Pro VC, sir, Janardhan, sir, and Registrar Putmadappa, sir, for their support in organizing this event. I also thank all my colleagues and dear friends who all helped in this event organization. Thank you all. Once again, thanks to all the participants here. Thank you.
Thank you. Thank you.
Thank you. Thank you, sir. Thank you very much.